Thanks everyone for coming. This is another ASA ECR sponsored symposium. Our speaker today is Radhika. She's from ANU. She'll be talking to us about the critical magnetic Reynolds number of the turbulent dynamo in collisionless plasmas. I'll let you take it away.
Thanks, Aman, and thanks, Nandini, for helping me put this visit together. So Aman told me that a lot of people from here are at Mount Stromlo this week, so I came from Mount Stromlo to here just to balance things out a little bit. So today I'm going to be talking about the work I've done in 2.5 years of my PhD. And this work has been done in collaboration with my supervisors, Amit Seta, Christoph Ferrat, and Matt Kunz. So I'll just quickly jump in then. So what is the nearest collisionless plasma to us? It is the solar wind. And how we parameterize collisionless plasma is by looking at the mean free path of this plasma and comparing that to a characteristic system length scale. So the mean free path, or lambda MFP here, is around 1 astronomical unit, which is the distance between the sun and us. And that's very close to the system scales that we are interested in, which means that particle in the solar wind does not encounter any other particle or scatter off any other particle until it reaches us. Another example, kind of far away from us, is the galactic center, where again the mean free path of this plasma is comparable to the system length scales that we are interested in, making this once again kind of collisionless. And finally, the astrophysical gas that I'm most interested in with my PhD is the hot gas in the intracluster medium. So this is a Chandra observation with some dark matter projection put on top of it. I think that's the blue one. And here again, the mean free path of a particle is pretty close to the system scale. Hence, all of these plasmas are collisionless. Now, talking more about the hot intracluster medium itself, it's extremely hot and it's extremely diffuse, which is why it makes it so hard for particles in the ICM to kind of collide or scatter across from each other. And this plasma also has a lot of chaotic mechanisms introducing turbulence into this kind of collisionless particles going around. So galaxy mergers, AGN jets, and so on. And we have observations of how much the turbulent speed of this gas can be. The turbulence in these kind of plasmas are primarily probed by X-rays, and there can be different modes of turbulence. So this can be either completely irrotational, so something that can be caused by gravity, and it's just like a zoom in, or a very rotational kind of mixing, which is like a swish swash motion. So it really depends on what physical process is driving turbulence, but this is turbulent and a collisionless gas. So finally, a final number that I'm gonna throw at you here is the Mach number of this plasma, which is the ratio of the turbulent speed to the thermal speed of this gas, and that is close to 0.1, making this a subsonic gas. So this is about the previous things I said was about the kinetics of this gas, but we also have information about the magnetic fields in such systems. So this is a coma X-ray map from Annalisa Bonaferre's paper in 2010, and all these like white contours are radio sources in this, and this particular paper looks at Faraday rotation and tries to figure out the magnetic field strength in the coma cluster. We also have simulations. So this is in this particular study, they use the ENSO code and they have galaxy clusters merging into each other in relaxed states and so on. So this one here is a relaxed cluster, and both of these are clusters looked at post a major merger in the gas. And you can see the magnetic field strength and the gas density. So we can see that these are pretty much microgas field strengths. Um, so this is again a plot of the magnetic field with the length scale from the same paper. So basically, we have microgauss field strengths on pretty large length scales that we observe galaxy clusters on. So the important and interesting thing with the microgauss level field strength is that this is close to the energy in the turbulence in these kind of systems. So the magnetic fields are have the same amount of energy as the turbulent gas. So then we can say that these are dynamically strong magnetic fields. But how do we get such strong dynamical magnetic fields in the ICM? So in a collisional MHD sort of plasma, we have the induction equation, which governs the evolution of magnetic fields. The first part here entangles the velocity and the magnetic field. It's called the inductive term or the inductive forces, and this is how if there is turbulence in this plasma, that gets entangled with the magnetic fields. We also have diffusion, and this term basically kills off magnetic fields. So, what happens to the magnetic field, the scales they are on, and the strengths they get to depend is basically governed by this induction equation. So we also know from theoretical predictions and other kind of estimates that we can have very small seed magnetic fields which are um, really many orders less than the magnetic fields that we currently observe. So like 10 to the minus 12 microgauss. So there can be, we know that there can be seed magnetic fields, but what we observe are much stronger fields. So how do we go from a very small magnetic field to basically a field that is so many orders of magnitude larger? So in collisional plasma and in magnetohydrodynamics, people have studied this phenomena called the turbulent dynamo. The turbulent dynamo basically injects energy from the turbulence into the magnetic fields, and this amplifies the magnetic field strength. So here, this is a plot from Seta et al. 2020. This shows the URMS, which is the red line. So it shows the turbulent speed, and BRMS, which is basically the magnetic field strength. So as soon as this mechanism starts off, there's a very sharp and quick exponential phase, which is the part that actually takes magnetic fields high up by like orders of magnitude. And then there is a transition. Here it's not so exponential, it can be linear, and finally, this all goes into a saturation phase where it just basically stays. And this depends on if the amplification mechanism or the inductive term kind of dominates over the diffusion term in the magnetic field evolution equations. So we can quantify this using the magnetic Reynolds number, Rm. It's just the ratio of the amplification to diffusion, and it looks like UL by eta, where eta is the diffusive coefficient, U is some characteristic turbulent velocity, and L is a length scale that you're interested in. So just from us wanting to see amplification win and seeing magnetic fields grow, we know that it should be greater than some value, which we call Rm critical. Here. So in a very kind of brief argument, how turbulence manages to amplify magnetic fields is that if you take a flux tube of the plasma, we can think of magnetic fields being frozen into this whole loop. And when turbulent velocity modes are introduced in this plasma, it can basically just stretch this flux tube out, twist it, and then fold it on top of this on top of itself. It can also do it in reverse. So basically, it depends on what turbulence does to these flux tubes. But in the final stage of this, these two flux tubes kind of merge on top of each other, and the magnetic field flux through this loop doubles. So for n cycles of this loop, this goes as 2 to the power n, or an amplification that looks very exponential. So it goes something like e to the power gamma t, where gamma is what I'm going to call the growth rate or amplification rate of this dynamo. So this is a very kind of generic process. People have looked at it in context of star formation in young galaxies, but coming back to the hot ICM and collisionless plasma, is any of this possible in collisionless plasma? And if it is possible, how is all of this different from what we get from an MHD plasma? So the fundamental difference between a collisional plasma and a collisionless plasma is the ratio of the mean-free path to the length scales that we're talking about. In a collisional plasma, which we often model with the fluid equations, the mean-free path is much, much smaller than the system scales that we are interested in, which means that it makes sense for us to define a bulk speed, or we can think of chunks of this fluid moving together. But when we come to the regime of collisionless plasma, we can't do that anymore. We have to start considering individual particle motions. And this is where we need new numerical techniques to kind of run simulations and understand plasmas like this. So this here is basically the regime of all MHD codes, and when we come to collisionless systems, we basically start resorting to a kinetic treatment, or in particular for my work, a particle in cell method. So have these simulations been done before, and do we know if this works at all? Yes, because there are two previous papers who kind of run these simulations. Both these works are slightly different from my work that I'm going to be talking about later in this talk. But if you see these two curves, these are evolution of magnetic energy as a function of time. The plot on the left is really overcrowded, but it is basically exploring this phenomena for a range of different initial conditions. And they do see very sharp jumps in the magnetic energy. And we are looking for something exponential here. So this was a very proof of concept study. Later in 2018, Sintonier and Kunz had this study where they looked at one particular simulation and they ran it longer. And here they could basically find a extended range in which we can fit an exponential growth curve. And this work shows more clearly that there is kind of a kinematic or exponential growth phase. And this collisionless turbulent dynamo is in fact possible. So this is where I came in 2021 when I started my PhD. a lot of my PhD has been writing this kinetic code within the Flash code, and it's Akash, abbreviated for Astrophysical Hybrid Kinetic Simulations with Flash, and Akash also means the sky in Hindi and a lot of other Indian languages. So it's a cool coincidence that worked out. This is a hybrid kinetic code, which means that we are not going to think of all our particles as all the plasma that we have as particles. We're going to think of the ions as particles and the electrons as a fluid. So this falls somewhere in the middle of the regimes of fluids and fully particle codes. Uh, of course, the evolution of this plasma now needs to be coupled with the magnetic field because that's what we are interested in, how the magnetic field evolves in this gas. And that comes through the Maxwell's equations in the non-relativistic limit. We've tested this code with particle evolution, wave propagation, wave particle instabilities, and so on. And we have a lot of state of the art things implemented into this code now. So this is in summary how a hybrid particle in cell code works. So we have ions as particles on the grid. This is the equation for updating the positions, and this is the one for updating velocities. So these charged particles are present in electromagnetic fields, so they're going to feel the Lorentz force, acceleration due to the electric field, and the magnetic field, kind of pushing them in circles. And once these particles change their velocities and their positions, their density and currents are going to change. So the density comes from the position of these particles, and the current is going to come from their velocities. And we need these quantities on the computational grid. So then we solve this very complicated Ohm's law, which gives us the electric field. And then we calculate the magnetic field from Faraday's law. And then we take the E and the P, which are updated now, and give it back to the particles. And this is basically one time step in the code. How this looks a little bit in real life is that if you imagine these black cells to be the grid and these red particles to red kind of dots to be these particles, you have grid centers where you can define things like the electric field, the magnetic field, velocities, and so on. And you also have these particles which can swoosh in and out of any cells as they please. And we have to make these particles and grids interact with each other. So if the position or velocities of particles change, then that has to be communicated to the grid via a grid particle to grid interpolation. And similarly, when we need to, for example, give the particle the magnetic field or electric field, we have to take that information and interpolate it back to the particles from the grid. So we do a couple of interpolations throughout that loop. And this is important because we want the particles to basically govern the evolution of magnetic fields. There's different ways to do this, but what we do is cloud in cell, which means that um, in a scenario where your grid does not change, you basically say that each particle kind of has a grid cell volume around itself, and how much the velocity or position of this particle is going to be kind of put forth in the calculation towards each grid cells is determined by how much of that particle cell is in that particular grid kind of volume. This is what we do in these interpolations back and forth. So some kind of typical length scales and time scales around the Earth's own magnetosphere. So on the left are the length scales, and on the right you can see the time scales. So on the top, where we can do fluid simulations, we find really large system length scales and really long time scales. And here we can solve the Navier-Stokes and all the MHD equations that we know about. At the bottom, where we really want to know what each individual electron does, we have to go into the full nitty-gritty of full particle simulations. And this is where a hybrid kinetic approach kind of lies. And you may ask me, well, then you should just do full pick or full particle and cell simulations. But the problem with going down this plot is that this is how the numerical cost of these simulations go. So a hybrid pick approach is basically trying to get some particle physics into your code, but also doing it in such a way that you can actually run these simulations. So I'm going to run through some quick tests that we did. So we know that if we put a charged particle in a magnetic field, it's supposed to go round and round. And this is the easiest sanity check you can do for a particle and cell code. So we tried that, and this is the map. This is a plot for the position as a function of time, and yeah, so we see that for the integrator that we use, which is the Boris integrator, the solutions from the analytical one basically match up to our numerical solutions. This is a test we did so that we can ensure that our code is energy conserving, which is problematic in the yellow simulations here. You see that the like Lama radius of this particle starts increasing, which is extremely problematic because we know that magnetic forces cannot do any work. So this should better not happen in a code. Another thing that can happen in collisionless plasmas is waves, and in particular, these systems can propagate alpha waves certain at certain points in the parameter space. So this one is basically a sine alpha wave, and you can see that this alpha wave sort of moves through the computational domain. The next one is basically a wave with k equal to 2, so it has like two bumps and two points, and this again like moves through the computational domain. So we check that we can in fact propagate waves. We also check the waves with different parts in this dispersion relation, and we find that what our code spits out is consistent with the analytical simulations and other hybrid big codes. So this was another sanity kind of check. And finally, we also do wave particle interactions. This is important because you have these bunch of particles which don't collide or talk to each other, but what they do is interact with the magnetic fields. And by talking to the magnetic fields, they can basically also start talking to each other. Uh, so this is a test where we basically show that dissipation of wave energy is possible into the thermal particle energy and so on. All right. So I did all that to run these simulations of the turbulent dynamo in collisionless gas. In order to do that, we take the earlier particle evolution equation and we add a turbulent forcing to this because that's our source of energy to amplify these magnetic fields. And this forcing field itself has been described in a lot of detail by this paper, Erat et al. 2010, and we inject this forcing energy on large scales. So it is calculated on the grid and then interpolated to the particles at their position. And we also do a purely rotational kind of forcing for these particles. So what we saw when we added turbulence to these particles is that the thermal energy of the particles, which is VTH, started growing very rapidly. And we could not achieve our target turbulent speeds as well, which is twice the trouble for determining the Mach number because we don't get the correct beta. Our V thermal keeps increasing. So no matter what you start with, you're going to get extremely subsonic very quickly, as you can see from the red curves in the quadrant panel here, which is the Mach number as a function of time. So the solid curve is for a Mach 3 simulation, which is supersonic, and the dashed curve is for a subsonic simulation. And in order to basically run these simulations, we also had to test and implement a new cooling method for this plasma so that we can basically get curves that look like the blue curves in here, and we get the target Mach numbers in these simulations. So how the cooling works is actually a really simple process. It basically looks at each particle, and it uh, calculates how hot each particle is. And you know the initial temperature because you set it, and we don't want that to change. So it basically just rescales the whole velocity vector and makes it shorter so that the temperature of this plasma does not change, no matter what we do with turbulence and other kind of things. So finally getting to the collisionless turbulent dynamo simulations, these are the initial conditions of this gas that we play with. So this is the Mach number. There's also the initial plasma beta, or the ratio of the magnetic to kinetic energy initially. So if you start with very small magnetic fields, this is going to be a very small number initially. And if in fact this dynamo is able to amplify things exponentially, then we should see a very kind of sharp rise. And the magnetization, which is something that's not required for MHD, but because we have particles in our simulations, this becomes important. So the magnetization is just the ratio of the Lama radius of each particle divided by a system scale. So in this case, we just consider the box length here, and it's just MV by QB. So if the particle is unmagnetized, that means that whatever Lama motion it may do subject to a magnetic field, you will not see this in your numerical simulation. It's just going to look like it's getting kicked around by turbulence. But I am kind of saying that magnetic fields will increase, which means that this ratio is going to decrease until it gets to a point where you can actually see these Lama gyrations in the box. So it will look like something is trying to gyrate in a circle and then gets kicked, goes to another place, gyrates again, and so on. So when you only see turbulent motions on these particles, that's what I'm calling the unmagnetized regime. And when you can see them like gyrating, and you can see the effect of magnetic fields on these particles. That's the regime I'm calling the magnetized regime. And it is important that we resolve the Lama radius of these particles the whole way through our simulations, which gets tricky if this is an exponential amplification. The Lama radius can kind of drop pretty quickly. So this is like analytical formula that I derived, which is required to resolve things as we run these simulations. And you can see a 1 by n, where n is the grid resolution here. So this means that in order to run these simulations longer and explore more and more parameter spaces, we really need really large periodic grids to do our simulations in. And this is what kind of makes our life difficult in terms of running particle and cell simulations, that these are in fact extremely expensive computationally and also have like a whole new set of challenges associated with running them. But we ran them. And these are 3D, looks like 3D plots from some of my simulations. So the orange color bar is basically the magnetic energy, and the blue color bar is for these magnetic field streamlines. And on the right, we see that if you have a magnetic Reynolds number high enough, you see these field structures kind of getting tangled within themselves. And this is what we would expect for an MHD dynamo as well, that the magnetic fields start getting twisted and stretched and folded from the influence of the turbulence. And you also see some small scale structure in the magnetic energy itself, which you don't see for a lower magnetic Reynolds number simulations. So this is a summary plot of some of these simulations. We run these simulations on 120 cubed grid cells, and these simulations have actually more than 100 million particles in total. We try to do a subsonic plasma close to Mach 0.3. We have cooling that we spoke about earlier, and these are all initially unmagnetized simulations, which you can see from the final plot here that they actually start with this ratio being greater than 1. So the first one here is the Mach number. The second panel is the magnetic energy, and the third one is just the same, but it's normalized to the kinetic energy instead as a function of time. So it turns out that it actually does work, and we do see exponential amplification. The black curves are sort of the growth rates that I measure in these exponential phases of the dynamo. So for higher RM, you see it pretty clearly, and as soon as it gets close to 100 or so, you kind of see this process dwindle down and like settle, which is the green curve here. And for even lower values of RM, you just see the field starting to decay. So this is the regime of amplification versus diffusion. You do need the RM to be greater than some value so that the amplification wins over the diffusion, and you can basically have exponential growth of magnetic fields. And we do find the existence of a critical number above which magnetic fields grow in such plasma. We can also talk about the kinetic Reynolds number, which is everything the same with the magnetic Reynolds number, except you have the viscosity involved. And the viscosity is something we cannot set in these simulations, unlike the MHD equations that we have, because we don't have a Navier-Stokes in which we can plug in this number. So the viscosity of this plasma is basically self-determined by whatever processes that happen in this plasma, and we really don't know where the RE or the viscosity of these simulations are. Um, But to kind of give a hint into the more kinetic side of things in these simulations, this whole setup uh, does not have any collisions, which means that it's not isotropic. It does not have a fixed value of, it does not have an isotropic value of temperature, pressure, and those kind of things. So we can start defining pressures perpendicular and parallel to the magnetic fields. And when we do that and we introduce turbulence in these kind of situations, you can end up with a flux tube, which is in kind of a kink to begin with, and you have parallel pressure increasing from both sides. Now, this is basically going to make this narrower and narrower until this whole system snaps and breaks apart and destabilizes. This is called the fire hose instability, and another one is the mirror instability, in which particles can get trapped in field loop designs, go back and forth. But if they have enough perpendicular energy, they can start swishing out of these magnetic field orientations that they are trapped in. And this also destabilizes the plasma. So the fire hose happens in excess parallel pressure and the mirror happens in excess perpendicular pressure. So we can quantify this by defining this quantity delta. So a delta greater than 1 means regions of this plasma are susceptible to the mirror, and less than 1 means that they're susceptible to the fire hose. So, in kind of a 3D model of some magnetic field streamlines that we have, you can see kinks forming where it's possible that the system destabilizes and breaks apart these flux tubes. And there's also regions where mirrors can be found. So, these kind of kinetic instabilities are actually what um, determines the viscosity of such plasmas. So we repeat our simulation setup with different values of Rm for different magnetizations. So we go from this ratio of 1000 to 1, and I've plotted the growth rate that I measure from these simulations as a function of the magnetic Reynolds number. They all show a very similar trend, but they also have a slightly higher critical value above which the dynamo is possible when this number decreases. And you also see that the saturation level here decreases, but yeah, I'll leave that discussion out. And we find that this behavior is pretty similar to what we know from MHD. We also tried another experiment where we changed the magnetic to kinetic energies initial strength. So you can do this, for example, by changing the initial magnetic energy that you start with in these simulations and decrease that, and that will give you a smaller value. And we look at the evolution of magnetic fields, and we find that the growth rate of this collisionless dynamo process does not really depend on this initial ratio. And this is again something which is pretty similar to the MHD uh, dynamo itself. So, in summary, a lot of things look very similar to what we know from MHD and collisionless plasma, but then there's also a lot of indications that things are different, and we actually need these particle in cell simulations. But a lot of the work that I spoke about in this talk is from this particular paper in review right now, uh, where we talk about how there exists an RM critical for this plasma, and how that compares to MHD. The code itself is another paper that I'm writing right now. This includes the whole setup, the algorithms and the tests and so on. And hopefully, I have the strength to finish this soon. But there's also a lot of other interesting questions with this gas. For example, can we actually calculate some value for the viscosity in this gas from our particle and cell simulations? And from that, we can determine a kinetic Reynolds number. And then, as the magnetic energy grows, what happens to this kinetic Reynolds number? Does it change? Does it stay the same? And this is where it can start to get pretty different from MHD. How does this behave when we start increasing the Mach number and we reach different regimes? How does it change with different types of turbulent driving and so on? So this is all future work that I hopefully get to. But that's all from me, and I'm happy to take questions now. And thank you so much for listening.
Thanks, Radhika. Are there any questions online first? Otherwise, in the room?
Thank you, first of all. And I'm sorry if my question is kind of ridiculous because I couldn't get how you define the size of the grid. And I'm kind of like, is it like a cube? Because in my mind, I'm kind of like the object you're working, it's kind of spare. It's not only a surface, and I'm kind of like, is it, for example, the size of the grid? It's kind of like when you have the same number density of particles, kind of like that. I mean, how do you define the size of the grid?
Okay, so
I'm kind of like the number of particles in each grid can be very sensitive to yes, the magnetic field and other things. Yeah,
you're absolutely right. So initially we just have this like 3D cubic cell, and then we can start placing like cells in here, right? So we can divide this whole cubic Cartesian system into smaller and smaller cells. But as you said, there are also particles which are involved, and they are free to move from whatever cell to whatever cell. So the whole grid stays fixed, and the only thing that moves throughout this whole process is the particles themselves. But for example, you can end up with a scenario where there's one particle in one cell and 100 in a nearby cell. That would mean that the gas density in that particular cell would have is going to be 100 times greater than this cell. So the grid itself is fixed. Things that change are because of the particles moving across themselves, and quantities like the gas density and currents and so on, those come from the particles, and those are like continuously variable things because these particles keep moving.
and the size of the cubes also are changing. Yes, from the core to the surface of the object.
So we don't have any like sort of AMR or adaptive mesh refinement, if that's what you're asking. Like everything is like a fixed uniform grid. So the whatever the like length size of the grid cell is going to be, that's going to be fixed from the initial to the end of your simulation. But AMR pick is like pretty interesting and also pretty complicated because once you have particles moving into like smaller cells, you can run into a lot of problems if like the particles.
Exactly. Because I was thinking about also the collision of other particles. Because you just mentioned that you work with electron and also ions, something like that. Yes,
we have just proton electron plasma.
Yes.
In this one.
Yes, and I was thinking if you have ever considered working with QFT2, quantum field theory, instead of Maxwell. They use Maxwell also in QFT, but I was kind of like, because this is working with particles, and if we just see particles as fields, not particle or not wave, maybe we can have more specific values for maybe velocities. It's just an idea. I don't know.
Yeah. Do you mean things like distribution functions? Yes. So people have actually looked into like a distribution function evolution. So this particular paper by Rincon et al. This plot is actually from such a study where they look at that. But with the distribution function, it has 3 space, 3 velocity, 3 time. So this is like a 6D simulation you're running in time, which as you probably know, even 3D can be hell, and then you go to 60. So it, but with the fixed simulations, you basically get away with this with just a 3D box, and you say the velocity space is actually sampled by the particles themselves. But yeah, people have actually done that as well. Yeah.
Great. Thank you.
Any other questions? Sarah?
So it was exciting to see that you can reproduce that the kinetic growth of the magnetic field with this method. In the MHD case, you have the kinetic bit and then the transition bit and then the saturation bit.
Yes.
Is that also true with this bit? Like if you ran it for longer, would it
Yes.
saturate?
Exactly. So that's a really interesting point. Thanks for picking up on that. So eventually, because turbulence itself is the mechanism that is pumping energy into this plasma, we cannot get to a situation where the ratio of the magnetic to the kinetic turbulent energy goes greater than 1, because that would mean that we are generating free energy somehow.
Fair,
So
okay.
as this third panel starts approaching 1, which it quite doesn't, maybe it does, we should start these curves kind of like turn over and then settle into something. And previous studies who have looked at this mechanism in saturation have found that the value at which this happens is actually 1. So the magnetic energy strength is in fact equal to the turbulent kinetic energy. And if that is in and that means that it is possible in a situation like the hot ICM where we find this kind of equipartition between the kinetic and magnetic energy strength. So it's very hopeful for the ICM.
That's cool. Can I ask another question?
Yeah.
So you just said, oh, so we inject some turbulent energy. I was wondering if you try to use particular physical, actual sources of turbulence in the ICM.
Yeah. So the short answer is not really. So we know that if this is going to be caused by something like a collapse in the ICM, then this is a compressive or non-rotational thing, and if this is something like a shock or like a bombardment, it can be a purely rotational kind of energy source. So we can control this on the scale of being completely non-rotational to a rotational force by this parameter. But that being said, I don't really know if the ICM actually has what kind of turbulent drivers are present in the ICM. So it'll be interesting to um, do a more physical modeling of these turbulence driving sources, because people have looked at this in MHD and found that it does actually change a lot for the growth rate of this system and the value attained at saturation and so on. So yeah.
Cool, thanks.
Nice.
Are there any other questions in the room or online? I might have one that sort of piggybacks off that one a little bit. I was also intrigued by, because I saw how all your equations worked, also, and then I was a bit intrigued by your injection of the turbulence force. So I was wondering, and this might be a misunderstanding, but is energy then sort of conserved in this box, or is that injection of turbulence force a bit sort of like just increasing?
Yeah. So the energy injected by turbulence is the sum of like if this plasma loses any like energy due to
Yeah.
viscosity plus how much you cool plus the magnetic energy.
Right. So that's those are the sort of the sources,
Yes.
and then they go just into
Yes,
turbulence.
there's
I see.
basically only like one source, which is the turbulence,
So,
and like the sinks are the plasma like just diffusing and losing energy, and like we are taking energy away from with the cooling as well, and some part of it also goes to the magnetic energy. So it might end up that you actually don't need as much turbulent energy, but we also have like viscous dissipation and other things we need to like combat with. We basically adjust the turbulent driving amplitude to make sure that we get the Mach number that we want. And that's how we can decide on how much energy we need to put in so that the kinetics of the system stays the same while everything else is allowed to evolve.
right. Yeah. No more questions? Nothing online? In that case, can we just thank Radhika one more time? And thank you all for attending the seminar. Thanks, Nandini, for helping organize and stuff.
Thanks, Nandini.
Probably going to do lunch again. I think that we have an in-person speaker, which is nice. So we try and provide lunch for you and students at Solar Origin. So